Hello, pre-calculus students. Today we're going to talk about 9.4, acceleration and deceleration. So let's take a look at this table below. And I'm realizing right now that when I made the PDF, you cannot see the names of any of these columns. So it says below are the estimates of the world population in recent years from the International Database of the U.S. Bureau of the Census. And this right here is, let's see if I can do this, the year. This is the world population. I'm going to type it, it'll be better. And then this is the average rate of change during the previous 5 years. So this is the average rate of change. I can type rate of change during the previous 5 years. And then this is the average rate of change of the average rate of change. So then you're probably like, all right, well, what does that mean? So when we say average rate of change, we mean the slope. So this right here is the slope. So it's the change, if we're using this data, the change in the number of people over the change in year. So this is the number of people divided by the year. So it's like we found the difference here, we found the difference here, and then divided them and got this. And then we found the difference, divided them and got this. So now what's happening here is that we're finding the people per year. So this divided by the change in the year. So it's the people per year per year. Okay, so it's the people, so it's our slope. So the people per year, and then it's the average rate of change of our slope then per year. So that's what this represents right here. So if we found like this difference here and then divided by the change in the time, it's the people per year squared. So acceleration is when we find the rate of change of a rate. Deceleration is when that value is negative. So like here we see it's going down, then it's deceleration. The instantaneous acceleration, or A of t, of a projectile. So remember, we've been talking about, first we talked about height, and then we talked about how the derivative of the height was the velocity. And now if we take the derivative of the velocity, so that's the rate of change of a rate, that's our acceleration of a projectile or other object at time t is defined to be the instantaneous rate of change, in other words, the derivative of the velocity. And so to compute it, we're going to take the derivative of the velocity v at time t. So if we just had any general equation for height, it's all the ones that are in feet are always negative 16 t squared plus the velocity times t plus like our initial height. You could put h sub 0 or our s value. If we went to find the velocity, which would be the derivative of the height, and then the units on this, for this right here, would be in feet. All right, for the velocity, if we took the derivative of this, we could use the shortcut we talked about last time. So we could do 2 times negative 16, so negative 32, and then reduce the degree of this by 1, plus, if I take the derivative of this, it's 1 times v, which is v, and then reduce the degree by 1, that's gone. And then this would just be a constant number, and the derivative of that is 0. So then this would be in feet per second. If we take the derivative of this, then if I do 1 times negative 32, that's just negative 32. And then I reduce the degree of that by 1, it's gone. And then this is a constant, the derivative of that is 0. And so then this is just negative 32 feet per second squared, which should make sense because that's our constant for the acceleration due to gravity. All right, so let's take a look at this example. It says find the instantaneous acceleration, A of t, of a projectile whose position at time t is given by, I hate it when this happens, h of t equals, this got bumped down here, 800t minus 16t squared. All right, so the height function is what's given. So we know h of t is this 800t minus 16t squared, and the height is in feet. That's given. The velocity is the derivative of the height. So if I take the derivative of that, that gives me my velocity. So this would be, if this is 1 times 800, so that's 800. When I reduce the degree by 1, that's gone. Minus 2 times 16 is minus 32t. Okay, so that is the formula for the velocity, and this would be in feet per second. The acceleration is if I take the derivative of my velocity. In other words, we call it the second derivative of the height. So if you take the derivative of something and then you take the derivative of the answer you get, that's called the second derivative. You could also sometimes take the third derivative, depending on the function. All right, so if I take the derivative of this, the derivative of a constant is 0, and then this would just be negative 32, and then feet per second squared. So then it says determine the instantaneous acceleration of the projectile at t equals 20. Well, the acceleration is always negative 32. If you think about the graph of this, if I were to graph the acceleration, which is through negative 32, so here's negative 32, and then at time 20, so let's say here's 20, the acceleration is always 32. So a of 20 is just negative 32 feet per second squared. So when you go to plug 20 in here, there's no variable. That means it's because it's constant. It's always negative 32. All right, so then here on this next page, it just reiterates that acceleration is the derivative of the velocity, or in other words, the derivative of a position, right? It's the derivative of the height. So because acceleration is a derivative of a derivative, acceleration is said to be the second derivative of position with respect to time, right? Which is like what we were just talking about. And so then it says, given an arbitrary function f, the derivative of f prime of f is called the first derivative of f. The second derivative of f is the derivative of the first derivative, denoted f double prime. All right, so here is how like what we just did looks. So this was our height function as a parabola. The derivative of something quadratic is something linear. So here's my line. That's the derivative for the height or the velocity. And then if I take the derivative of that, which is just a constant, then this is the graph of the acceleration. All right, that's it for acceleration and deceleration.